I still see that there are some people who have not taken that elementary mathematics test, which is again, of course, closed because you had time until yesterday evening. So I don't know what to do about those people. I might, of course, automatically add them to the course and then make them do this by force. That's one option. But if you want to avoid having to take elementary mathematics, then you should try this elementary mathematics diagnostic test. It's all for you. It's not something invented because I want more work. I don't want more work. But unfortunately, some of you have either forgotten school mathematics or never were that good at school at all. So you need to have a catch up course. So those of you who have not done it, well, I will open it at some moment later today, evidently, but elementary mathematics is for you. It's not. This course might be for me, but elementary mathematics is absolutely for you. All right. So now I'm going to close the camera, not to this, so I don't distract myself
Hello, madam.
by looking
We can't
everywhere.
hear.
And so we will go on to the inverse matrix. Let me remind you to write your names in the Zoom meeting chat. Please use the option, the message everybody, because I have two identities, or actually it's the same identity from two computers. As I keep saying, please write it in the chat meant for everybody because I might not be able to notice it. Not
Madam,
clear audio. Why is that?
ma'am.
Okay,
Good evening. Hello.
I will try to switch to my other computer audio. Let's wait. All right. So how is this? Is this better? I'm now trying to go through the other computer. Can you hear me better now? All right. So I will leave the audio from this computer. Okay. And I will switch off the speakers on the other computer because the echo otherwise is too bad. All right, so I'm going to use audio from one computer and do the presentation itself from the other computer. All right, let's try it this way. So let's go back to the slideshow from beginning, and there we go. Okay, nice. So last time we started talking about the inverse matrix. I am again, as is my habit, I will try to run through the main points at the beginning so that you remember where we are and what we did, and then we will simply go on. Mostly today, we need to consider some examples for the inverse matrix. That's one thing. And the other thing is to consider another method for finding the inverse matrix. There are several methods, of course. So the cofactor method that we discussed on Monday is one, but there's another one that, let's say, links to our determinant method of row reduction and also links forward to Gauss method in solving linear systems. So that's an important one as well, mostly for practice rather than from practical purposes. However, there are people who prefer that method to cofactors. Especially if the matrix is large. For example, 4 by 4, finding 16 cofactors, each of them 3 by 3 determinant is not very pleasant. It's a lot of work. So in that case, it might be more convenient perhaps to use this other method. So let's go on, or rather back at the moment. So the definition of the inverse matrix was the matrix whose product, okay, I still haven't corrected this, whose product by the original matrix is the identity matrix. So like this, inverse matrix multiplied from the left by the original matrix, or from the right by the original matrix, would always give the identity matrix. The inverse matrix therefore serves the same purpose as, let's say, reciprocal numbers. Two numbers that are reciprocal, for example, 3 and 1/3, have the product 1. Similarly, the two matrices that are inverse get the product, the identity or the unit matrix, which serves exactly the same purpose with matrix algebra. And of course, the size of the matrix and its inverse will be always the same. Now, the cofactor method was dealing with finding cofactors for every element in the matrix, but before that, we needed to find the determinant. Remember, there was this moment of division by the determinant, and if the determinant is 0, we cannot divide by it. So that means that it's a special situation. So finding the determinant is always the first step. Then we find all the cofactors. Then we find all the cofactors of the matrix and form the cofactor matrix C of the given matrix. In other words, for example, for the matrix 3 by 3, the cofactor matrix would be C11, C12, C13, C21, 22, 23, and C31, C32, C33. So this would be the cofactor matrix. Cofactor matrix of the given matrix A. That is, every element is substituted by its cofactor. Every element is substituted by its cofactor. A very common mistake for cofactors, sometimes people get confused with determinants and start multiplying by the elements themselves. No, cofactor is a minor, just the minor, with perhaps that extra minus sign. And then the next step, transpose the cofactor matrix. Remember that what that meant, flipping the cofactor matrix across the main diagonal, across this diagonal. So we flip the cofactor matrix symmetrically, and then we get the C transpose, which is also called the adjoint matrix of A. Adjoint, and written as ADJ of A. Adjoint matrix of A. The adjoint matrix of A is almost already the inverse. What else we need is the number reciprocal to the determinant. So we take the adjoint matrix, which is almost the inverse, but we also need to multiply it by a number. This is the number. Let's not write matrix divided by a number, because that's not exactly mathematically, let's say, correct or a nice way of writing this. So the reciprocal of determinant, of course, it only exists if the determinant equals does not equal 0. So if the determinant equals 0, then the inverse does not exist. And we call this matrix singular, as in single without a partner. So we could think of the two matrices that are mutually inverse as partners. So a singular matrix would be a single one. Also remember that the inverse matrix, this relation between the matrix and inverse matrix is binary. That means it's mutual. If A is the inverse of B, then B is the inverse of A. So it's never just an inverse matrix. It's always the inverse of something. And secondly, the two matrices form a pair. They are usually inverse. So one is the inverse of the other, and the other is the inverse of the first matrix. So that was, let's say, this is the theoretical part. Now on to the practical part. So for the case of the 2 by 2 matrix, finding the inverse was very easy. Now I know it's in the bottom right side of the determinant. So notice that what we have to do is we have to exchange the elements A and D. They exchange places, and the elements B and D, these two elements, only switch the sign to opposite, but not the places. So A and D exchange places, but B and C change signs. And that is the adjoint matrix. That is the adjoint matrix. Yes, you of course still can use the cofactor method, understanding that now cofactors are single elements with perhaps opposite signs. Then transpose it and then multiply by the reciprocal of the determinant. Again, remember that the determinant has to be found and it cannot be zero. So if the determinant happens to be zero, then there's no inverse for the 2 by 2 matrix. Then the next thing that we did, we had an example last time. We found the inverse of this matrix. And then we had the inverse of this matrix. We already had the determinant before. And then I illustrated rather slowly, rather quickly actually, because there was not much time, I think. I didn't have anything else. Yes. We didn't have much time, so I actually was in a hurry to demonstrate the cofactors. So let's do the cofactors for this matrix one more time, more slowly. It's the same thing that is in the lecture transcript. By the way, I uploaded new files for lecture 2 and lecture 3. Now these should contain the answers. If you want, you can check, but perhaps not at this moment exactly. So the cofactors. Cofactor 1 is the minor, and so it is 0, 5, minus 1, 2. We already saw that, and that value is actually 5. 0 minus negative 5 is 5. The cofactor 1, 2, remembering the sign diagram, has to have a minus in front, but it's not multiplied by anything else. So the cofactor 1, 2, that's for this element. So we eliminate, we cross out the first column and the first line, first row, second column, and the remaining elements are 4 and 5 and minus 2 and 2. So 8 minus negative 10 is 18, but the extra minus in front makes it negative. And then we have, of course, cofactor 1, 3, which is in the plus position, as we can see. In the plus position, that means we don't change it, we don't change the sign, but eliminating first row, third column, we have 4, 0, and we have minus 2, minus 1. Which is minus 4. And then, if we place things correctly, then we don't have to write the matrix C as it is, because we already see the elements in the correct order. So you save yourselves a little bit of time of writing down the matrix. I know that some people prefer to write all those cofactors in one row, but then it's a little bit difficult. If you write them in the form of table, it actually is sorting things out. I know that some people even prefer to write the cofactor matrix, begin with this, and then they do this. See how it goes, writing a huge matrix without first solving the cofactors, and then we have minus there, and without the minus there. See, it's a huge matrix, but it works. If you write the corresponding cofactors, first of all, in a huge matrix, and then all that it takes is just write down just write down the values. It also works because it tells you the correct order of things and the correct signs of things. This is actually a good method to do, but don't forget the minuses. The minuses in a 3 by 3 matrix are only in 4 places, as you can see, in the middle of each side. So that's not so difficult to remember. But another option is not writing this in the form of matrix, but just making this thing like a table. So minus, so the cofactor 2, 1 is if we eliminate second row, first column, so 2, 1 element is this, we cross out, we eliminate that row, that column, and the remaining elements of the matrix 3, minus 1, minus 1, 2 form the cofactor. 6 minus 1 is 5, but an extra minus in front will give you a minus 5. Cofactor 2, 2 keeps the original sign because it's in the plus position. Because why the first one is not minus 5? Because the determinant is formed by AD minus BC. BC minus 1 times 5 is negative. Subtract negative 5, you get positive. Remember, we are subtracting a negative number. Minus 1 times 5 in the first cofactor is minus 5, but it is to be, you see, subtracted. And that's how we get the plus. C22, that's the middle element. So we cross out the middle row, middle column, and the remaining elements are 2, minus 1, minus 2, 2. So we have 4 minus 2. This is actually 2 because now minus 1 times minus 2 is positive 2. So we subtract 4 minus 2. This is a positive number subtracted from 4. And cofactor 2, 3 is again in the minus position. It's again in the minus position. And therefore, we have to put a minus in front, and 2, 3. So we think this has to be eliminated. Eliminate this row, eliminate this row and this column. And we have 2, 3, minus 2, minus 1. 2, 3, minus 1, minus 2, and minus 1. And that would be minus 2, subtract negative 6, means minus 2 plus 6, it's 4, but this extra minus in front gives us a minus 4. So in this case, we have negative 2, AD is negative 2, minus 2, subtract negative 6 means minus 2 plus 6 is 4, and the extra minus makes it negative. Next, the last row, C3, 1, third row, first column, that's the element minus 2. So we eliminate first column for third row, and we have clearly 3 minus 1, very visible, 0, 5, well, visible except for my scribblings on the matrix. I will erase them now so that we can see the matrix clearly, like this. So C31 actually means, okay, give it to me, pen. Okay, 3, 1 is this element. To get its cofactor, we eliminate that row, that column. Here we see it clearly. So 15 minus 0, absolutely 15. This cofactor 3, 2 is in the minus position. This is the minus position. So we eliminate that row, that column. Now we have these elements remaining and the extra minus in front from the sign diagram. So we have 2, we have 4, we have minus 1, we have 5. So it's 10 minus negative 4. 10 minus negative 4, it's 14. And the extra minus now makes it negative. And finally, the last cofactor 3, 3, which is in the plus position. And eliminating last row, last column, we get the minor 2, 3, 4, 0. 2, 3, 4, 0. So it's 0 minus 12. It is minus 12, negative 12. And here we have the cofactors already sorted in the correct order, which means that the adjoint matrix is now the transposed matrix of cofactors, which means I take the numbers from the first row. I'll change color. Let's take something bright. Okay. From the first row, and I put them in the first column. 5 minus 18 minus 4. And you see it's the same thing. And then we take the second row and make it the second column. Minus 5, 2, minus 4. See, it's there. And the third row becomes the third column. That's 15 minus 14 minus 12. These values put vertically and in the same order. So you see, this is how we get the adjoint matrix or the cofactor transposed matrix. And then to get the inverse, all we need is to multiply by the reciprocal of the determinant minus 1 over 40. And then, as we saw on Monday, it's all right to multiply the whole matrix by minus 1 over 40 if the number is nice enough. If you have something like 1/17 or 1/11, as we already saw in the 2 by 2 matrix last time, then perhaps we want to leave it in front. But otherwise we can bring it inside if the numbers are not too bad. Okay, the cofactor matrix, I didn't write it at all because I have it in yellow on the in the top right part. So it will be the same. And finally, the rest of it that I already wrote by hand. I already wrote all this by hand. But all right, I will erase now. I can erase the scribblings. Okay, erase all ink, and there we go. So we found the cofactor matrix, then we didn't even have to write it because we had all the cofactors put in the correct order very nicely. Each cofactor was replacing the element of the matrix already there in the table. Then we very quickly rewrote it, rearranged it to get the adjoint matrix, and all that remained was multiply by 1 over minus 40. And this is where we stopped. And now we have to do practice. So the inverse matrix for this 2 by 2 matrix. So if this is the matrix A, then the determinant of the matrix A, remember that we write the determinant between straight lines. Matrix is never written between straight lines because the meaning is completely different. This is the matrix with all elements, but the determinant is a number. And therefore, yes, we must use different notation. So it's 4 by 1, that's 4, minus 2 times minus 3 is negative 6. So the determinant of this matrix is 10. Then let's find the matrix A inverse altogether. Yes, the determinant is 10, exactly. And let's remember, it's 1 over 10, 1 divided by determinant, because it's important, it's not 0, so everything is all right. And now let's remember how we rearrange the elements in 2 by 2. It doesn't work for 3 by 3 or higher order matrices, but it does work for 2 by 2. So the elements on the main diagonal, 1 and 4, swap places, and the elements on the secondary diagonal only change sign. So from 2, we get minus 2, from minus 3, we get 3. So we have 0.1 minus 0.2 if we simply divide by 10 everything. So this is easy to write by multiplying by 0.1, that is 1/10, and this is the inverse of the given matrix. We can check, and actually I would like to check this. I would like to check this. So yes, this is interesting how you write down the matrix in chat. That's yeah, that's fun. So perhaps we can push the 3-4 line forward, put some spaces before 3-4, and then it would be absolutely perfect. Okay, let's check. Let's check that these are indeed inverse matrices. So let's multiply 4, 2 minus 3, 1, and let's multiply it by the matrix 0.1 minus 0.2, 0.3, 0.4, simply for the sake of checking. So let's remember how we did this. Let's remember how we did this. Laser. There we go. So for the first element, we go through the first row in the first matrix and first column in the second matrix. That would mean 4 times 0.1, 0.4, plus 2 times 0.3, that is 0.6. First column, second row, that would be minus 3, 1 multiplied by this first column in the second matrix. Minus 3 times 0.1 is minus 0.3, and 1 times 0.3 is 0.3. So those who have joined us late, I'm doing this mostly for the sake of people who missed last week, because I understand that some of you know matrix multiplication already quite well. So remember that we multiply pairs of elements, and we always go through columns in the second matrix, vertically through the second matrix, and horizontally through the first matrix. And we write the product evidently in the corresponding row, corresponding column of the resulting matrix. We multiply one element by one element, then we hop on horizontally or vertically to the next elements, multiply those, and then add. But evidently, you do need to read up. That's actually lecture 1, the first file. Those who missed it last week, please read up, because this is essential to be able to multiply matrices. Now, first row, second column would be 4 times minus 0.2, that's minus 0.8. Then going onwards, 2 times 0.4 is 0.8. You see, you have the 0. And finally, the last one, second row, second column, minus 3 times minus 0.2 is 0.6. And 1 times 0.4 for 0.4. So yes, we have 1, 0, 0, 1. So this is indeed the identity matrix. So we have checked. You will have a similar task. You will have a similar task in your home assignment. I will post. I'm not sure if I can do it today. Maybe it's only. I might only have time on Friday to do this, but that's okay, because the first unit test is next Friday. So I habitually give 1 week to complete the homework. If I post it today, then the deadline will be next Wednesday. If I post it tomorrow, then the deadline will be next Thursday, and so on. I will, in the end of this lecture, I will talk a little bit about handing in assignments, handing in work, formatting work, and all that in the online mode, because evidently, if we were in class, I would actually welcome things written on paper. As we are not in the classroom, then I have to manage somehow the files you send, and we will talk about it a bit later. Okay. So a little bit of respite. One more thing, we could have done this check. This way. Take the A inverse in this form. So in here I had A times A inverse. I can have A inverse times A, and I could write 1/10 times 1 minus 2, 3, 4. I will not do it completely, but I'll just show. And now A for 2 minus 3, 1. And I could first multiply these matrices because they are integers. Of course, it's easier to multiply them integers, because actually if you do this very simple thing by calculator, it is confusing and you might get confused about which numbers you are multiplying at which point. It's enough to miss one key, miss one number, entering one number entered erroneously, and you get the wrong result. So in principle, 2 by 2 matrices, very definitely you should multiply them on paper. Same goes for 3 by 3 attacks. So you could actually multiply these matrices, and you would ideally get 1/10 still outstanding, and you would get 10, 0, 0, 10, and then multiply by 1/10, and of course get the identity matrix. It is actually more convenient, and I sometimes wonder why people don't use this more, why they insist on doing this the hard way, when you can actually multiply integers and only afterwards multiply by that extra outstanding constant. Okay, so this was 2 by 2. Now let's move on to the next. This is a 3 by 3 matrix. We could do one exercise with this, and then I think not this, perhaps. We'll see there are quite a few of these matrices. So what I would say is that it would be good if you could practice finding them on your own at home. Because we can't do absolutely everything in classroom. We could do many things in classroom if you could manage somehow, if you could master writing on the screen. That is, if you have a touch screen on which you can write easily, because using the mouse for writing on the screen, yes, technically, of course, you can write on the screen, but using the mouse or even using the touchpad of a laptop, which is small, is rather difficult, and well, those of you who have the possibility of a touch screen and attempt to write on my screen, that would be nice. Yes, like pen, if you can, then I absolutely welcome your additions to the screen, of course, but I understand that not everybody has that possibility. And so let's find one inverse matrix. Okay, we need to find the determinant. Now, okay, how do we find the determinant in a good way, in a convenient way? So in principle, the habitual thing to simplify the determinant of this matrix would be attempt to do row operations. Row operations are, let's say, a better habit than column operations, even though sometimes the column operations are easier. So we could say row 2 minus 2, row 1 in the second row. So 1, 2 minus 1. Now let's make a 0 here. That's why we multiply the first row by minus 2 and add to the second row, because we want to make a 0 there. And this is the only option available to us. It's the only thing allowed. That is, multiply one row by some number and add it completely to the other row. So 1 times minus 2 is minus 2, plus 2 is 0. That's my purpose. Now, next element, 2 times minus 2 is minus 4, added to 5 is 1. Minus 2 times minus 2 is 2, added to 1 is 3. And to get a 0 here, we could say row 3 minus 3, row 1. So if I want to make a 0 instead of 3, I can take first row, multiply by minus 3, and add it down to the second row. I choose first row because it has 1. The element 1, as we see, is very, very useful because we see the constant to be multiplied easily. So 0, 3, 2 times minus 3 is minus 6, add down to 6 is 0, and minus 1 times minus 3, minus 1 times minus 3 is 3, added down to minus 2 is 1. We have the determinant in the diagonal form. We are very, very lucky with very little effort. So it's 1 times 1 times 1, it's 1. The determinant is 1. So I am just reminding you how the row operation method works. As I said, it is important and it will be important in the future as well for future methods. Of course, you could do it traditionally using the standard method, for example, by the additional columns. So I am reminding this as well, because this is sort of practice session today. No new material, just practice, practice, practice. Again, for the sake of those people who missed last week. For the sake of people who missed last week. For 3 by 3 determinants only for 3 by 3 determinants, I will use a different color, green, let's say. 1, 2, 3, 2, 5, 6. The 3 by 3 determinant can be found by adding the 3 products of 3 numbers going in the main diagonal direction. So that's 1 times 5 times minus 2 is minus 10, plus next product, 2 times 1 times 3 is 6, plus next product, minus 1 times 2 times 6, actually it's minus 12, and then subtracting the 3 products in the other direction. So these would be subtracted, but we generally subtract them in parentheses all at once. 3 times 5 times minus 1 is minus 15, 6, 1, 1 is plus 6, and minus 2, 2, minus 2, 2, 2 is minus 8. And now we can actually find this determinant. Evidently, this is minus 22 plus 6. And here we could say plus 15 minus 6 plus 8. Don't forget to change the signs when opening parentheses. And in principle, you would still get 1. So negative numbers minus 28. Positive numbers 21 plus 8 is plus 29, we still get the same 1. So this is about finding determinants, especially for those who missed the last week. Because last week we were dealing with determinants of 3 by 3 matrices. So here we have one method, very simple, just copy some elements, draw some lines very carefully, and add, subtract some numbers. So the green numbers, the green products are added and the red products are subtracted to get the determinant 3 by 3. I wrote 3 by 2, 3 by 3. And another possibility is applying these very special row operations. We can attempt to create some zeros. My purpose was actually to create only the zeros below 1. And then I would have 1 times the determinant this. So if I expand through the first column, I would have 1 times the minor 1301. But it turns out that we also got accidentally, in this case, 0, another 0 in exactly the right place to make the diagonal, the triangular form, which actually was very helpful. However, in another mode, I would simply take this element, multiply by its minor cofactor, whatever number I would get there. It would be still easier than finding the big 3 by 3 determinant. However, this is not so very complicated. So you can choose your methods. You can choose your methods for finding determinants. In the unit test, in the midterm examination, I will not ask you to choose any specific method. You may choose methods that are convenient for you. So we have now the determinant. I will now erase this stuff. And get back to my white chalky pen. So we now know that the determinant of this matrix is 1. That's very good. And now we find the cofactor matrix. Now we find the cofactor matrix of this. So I could say for the cofactor C11, this is the element. So plus, minus, plus. Again, that's the plus position. This is something I draw on the board every time because, well, if you don't remember in any other way, then this is how you might remember if I keep pushing it at you all the time. So it's the minor of this element. Remember how we did it? We mentally cross out that row, that column, and what remains forms the cofactor. The next one will have this minus, crossing out the corresponding element 2 and its rows and columns. What remains is 2, 3, 1, minus 2. Now, cofactor for this element, this was minus 1. I have to erase the unnecessary markings because otherwise it does get confusing. I know. It does get confusing. And here we have pen. And here we have for this, if we erase this row, this column, or erase or mentally delete, we have 2, 5, 3, 6. Then for the second row, first column, we have the minus position. Therefore, we put a minus in front of the minor, and that will be our cofactor. So minus, and now we delete that element, the row and the column. So we delete according to this. All right. So what we have is 2 minus 1, 6 minus 2. And this is actually a very good idea for writing down the cofactor. Why not? Now for the middle one, the sign is plus, the same sign. Delete middle row, middle column. We have 1, minus 1, 3, minus 2. Here we again must put the minus position. Delete second row, third column, and what remains is 1, 2, 3, 6. Here, plus position, so we only delete and see 2 minus 1, 6 minus 2. So this shows you very clearly what you have to do to find the cofactor matrix. And this is actually a very nice approach. So delete third row, second column, and we have 1, 2, minus 1, 1. And finally, last row, last column deleted is 1, 2, 3, 6. This is interesting. Actually, you might see some connections here. You might see some patterns can be noticed. Here. I don't like this one. Something wrong with that. So let's see. Delete this and this. No, this is correct. So this is perhaps wrong. Third, yes, this is wrong because in the third row we had to delete third row. So just a moment, let me correct. These are wrong, I think. No, 6. Yes, this has to be 6 minus 2. How is that? No, for this element we delete this, and we have 2 minus 1, 5, 1. Sorry, I think I made a little bit of mess with all my crossings out. I will expel all these. Okay, yes, right. Oh, perfect, write it. Yes, do it. Just do it, yes. All right, and in the last one, we deleted the last row, last column, 1, 2, 2, 5. Okay, Now, we can find the values, or we can find the values and already put them in the adjoint matrix, in whatever way you like. I generally prefer to see the cofactor matrix values as they are and then rewrite. So minus 10, so the first one, minus 10 minus 6 is minus 16. Minus 4 minus 3 is minus 7, but with this additional minus, it becomes plus 7. 12 minus 15 is minus 3. Minus 4 minus negative 6 is minus 4 plus 6, that's 2, but with the extra minus, it becomes minus 2. Minus 2 minus negative 3, minus 2 plus 3 is 1. 6 minus 6 is 0, change sign, it's still 0. Now, 2 minus negative 5 is 7. 1 minus negative 2 is 1 plus 2 is 3, change sign, minus 3. And 5 minus 4 is 1, sign is not changed. So this is the cofactor matrix. Now I can, in fact, write the adjoint matrix of this given matrix. Let's call this A. Adjoint matrix would be minus 16, 7, minus 3, minus 2, 1, 0, rewriting rows as columns with the corresponding numbers, of course, in the correct order. So A inverse will be 1 divided by 1 because the determinant is 1. So it actually, in this case, is this very same matrix. So times adjoint, I forgot, times adjoint matrix of A. So as a result, we have this very matrix, minus 16, minus 2, 7, 7, 1, minus 3, minus 3, 0, 1. So it is a bit of work, but finding the inverse matrix generally by whatever method involves work. It's never just automatic. It's never just very quick and easy. So yes, it basically involves a page of working. That's how it happens. All right, this is the inverse matrix as it is. And we are about halfway through the lecture. Good. So we will, now I have to delete this because it was done by a different method. But that's okay. That's okay, annotation is still good. Let's not do this, One of these matrices, I don't remember which one, I think F. Yes, F is singular because the determinant is 0. The determinant of this matrix is 0. You would discover it if you, for example, tried to eliminate the numbers 2 and 3 in the first column making zeros. If you wanted to make zeros there, you would very quickly discover that row 3 minus 3 row 1 actually gives you 0, 0, 0 row. And remember that the determinant that has a 0, 0, 0 row equals 0. So in fact, I could say that the determinant of this matrix is 0. So there is no inverse. It doesn't exist. It's singular. So this is a singular matrix. That was example 2F, the exercise 2F. So sometimes this is why it is important to start by finding the determinant, because imagine you do all that other work, find the cofactors, and then in the end find the determinant, which turns out to be 0. So all the work for nothing, which means it's always important to find the determinant at the beginning, because that's one of the main characteristics of a square matrix. All right, so how to deal with this? Show that the matrix N, which is made in this fashion, is the inverse of the matrix given matrix M. So there are two ways of doing it. For example, we will need to construct this matrix anyway. We have to find the matrix M. So to find the matrix M square, we need to square the matrix M, which means we multiply. What I very strongly advise you, yes, you are perfectly right, but my point is write the matrix twice, because if you have to perform the operations of going through rows and columns simultaneously, and if you are thinking within the same matrix, in the same spot, overlapping, so to say, your mind usually cannot process this. Your mind usually cannot manage it. And therefore, I would strongly advise to write the matrix. Actually, write it twice. Write the product matrix times itself. That's because otherwise it's so easy to make the error. I make that error. I am lazy. I try to do it all the time. And basically, almost always, I make an error and I have to redo things because it's very difficult to find that error. And so doing this, if we move, let's take the highlighter, through the first row and the first column, so we find the sum of the products. Okay, why doesn't it give me the pen? Nice. So we can of course now practice a little bit, doing this thing a little bit faster. I will not write the product. So 3 by 3 is 10. I'm only writing the finished product. 3 by 3 plus 2 by 1 plus 2 by minus 1. Second row, first column. So second row, first column. 1 times 3 is 3. Minus 2 times 1 is minus 2. And 1 times minus 1 is minus 1. I'm moving through the second row and third column. And now I'm moving through the second row and first column. And now I'm moving through the third row and still the first column, because I'm still in the first column of the resulting matrix. 3 times minus 1 is minus 3, plus 1 times 1 is 1, minus 1 times minus 1 is plus 1. So in this last thing, I did these elements, multiplication, addition of these elements. Now, the next step, I'm moving through the second column and all 3 rows. 3 times 2 is 6, plus 2 times minus 2 is minus 4, plus 2 times 1 is 2. That was first row, second column. Now, second row, second column. 1 minus 2, 1 times 2 minus 2, 1. 1 times 2 is 2, minus 1 times minus 2 is plus 4, 1 times 1 is 1. Third row, second column, minus 1 times 2, plus 1 times minus 2 is again minus 2, minus 1 times 1 is minus 1. Third row, second column. And finally, all rows, third column. Third column, now we are taking this now. 3 times 2 is 6, plus 2 times 1 is 2, plus 2 times minus 1 is minus 2. Second row, third column, 1 times 2, minus 2 times 1, 1 times minus 1. And third row, third column, minus 1 times 2, plus 1 times 1, minus 1 times minus 1 is plus 1 again. So this is m squared. So this would be 9, 0, minus 1. I'm doing arithmetics now. 8 minus 4 is 4. This is 7. This is minus 5. And this is 6. And this is minus 1. And this is 0. So this is m squared, matrix M multiplied by itself. You see how this would be very difficult to do if you were dealing with arrows and going through the matrix in the same matrix in 2 directions. And it's so easy to get confused that in general we always write the 2 matrices identical. Yes, they are both identical matrices side by side, and there we go. Now the next step to do Okay, I will erase this so that we see things more clearly. The next thing to do is subtract 8 identity matrices. So let's write 8i. Let's just write 8i. So 8 identity is. Okay, write it. Okay, write it. All right, it's 8, 0, 0, 0. Okay, 8, 0. Of course, we multiply. And all right, excellent. So this is the 8 identity matrix. As you write on paper, it would be actually quite nice if you write it below, somewhere close, so that you see how you add these matrices or subtract. In this case, you would need to actually subtract. So the matrix N is now M squared minus 8i, which means 9 minus 8 is 1, 0 minus 0 is 0, minus 1 minus 0 is minus 1. Now 4 minus 0 is 4, 7 minus 8 is minus 1, minus 5 minus 0 is minus 5. And the third column, 6 minus 0, minus 1 minus 0, and 0 minus 8. As we perform these operations. And now, how do we show that this is the inverse? Two options. One way, we find M inverse by classical method. Secondly, the other option is multiply M times N and check that we actually get the identity matrix. So I would vote for multiplying the matrix M and the matrix N just to check that we really get the identity matrix. So in principle, we should say that N times M, we should verify, is the identity matrix. We should multiply the two matrices. At this moment, I am not going to do that. My aim was, first of all, yes, indeed, I did want to remind you how to multiply matrices. This is the second time today. I am not going to do it for the third time. That's something you should do by yourselves. And if you do things correctly, you should get the identity matrix. This one, like this. That would be a good idea if you could try it and check it by yourselves to practice. But the other purpose was sometimes people get confused. So what's this N? What do we do with this? We simply construct this matrix according to the, let's say, formula. We have a formula. Okay. Okay, next. All right, now I have to, okay, I will do this. Oh, you did it by yourself. Okay, good. So in this case, you should again take the square of the matrix C. So you would multiply the matrix C times C, and then find C inverse. That is interesting. How is that? How can we use this to find C inverse? Well, the thing is, this C matrix is special. You cannot do it with any old matrix. Just square it and that will give you the inverse. It doesn't work that way. But this matrix is special, so if you take the matrix multiplied by itself and you get this C square matrix, you will see that it actually is pretty, well, it will be interesting. You will see from the C square, if you do it correctly, you will be able to see how you can find the C inverse matrix. A little bit of thinking. So this is, let's say, a question of type, let's say, well, maybe for a 10, that demonstrates how you think. You can show how you think by solving this kind of problem. Next, come on. Okay, new method. Because we have half an hour, 30 minutes remaining, there's another method. How to do the row reduction method. So sometimes Well, some people don't like finding cofactors, although we generally do need it. But row reduction method, as I keep saying, is in principle very useful because it is a whole method for solving systems of equations. It's a Gaussian elimination that is based on row reduction. And therefore, this method is important to practice, which is why we are also finding the inverse matrix using a similar method. So what we do is, suppose we have this matrix given, but we draw a vertical line and write the identity matrix behind that line. So now we have a double matrix, a big one, not 3 by 3, for example. It works for any size. 2 by 2, 3 by 3, 4 by 4 works always. And so not only the echelon form, so echelon form by row reduction, that's for Gauss method. That's for Gauss method. But for finding the inverse matrix, we do even more. We use row operations to transform the matrix A to I, to the identity matrix. And by magic, it can be proved, but by magic, when we do this with row operations simultaneously in the whole double matrix, they simultaneously will create the matrix I into a inverse. In other words, you should, by these row operations, what you should get is the identity matrix on the right hand side, and then you will see the inverse matrix, so identity matrix on the left, and you will see the inverse matrix on the right by magic, or no, by mathematics, of course. But the trick is to do the row operations, these operations, to the whole matrix simultaneously, the whole long row, not only on the left-hand side, not only to A, but also on the right. This is why we only use row operations, not column operations. Although in principle it would be possible to use columns, but for Gauss method, for instance, for linear systems, we cannot use columns. And that's why we generally use only row operations. All right, so what is allowed? So how do we make this echelon form by row reduction? What we can do is we can exchange two rows. It doesn't change anything. So unlike determinants, remember, in determinants, when we exchange two rows, the sign of the whole determinant switches to the opposite. Not so in this case. Not so in this case. Here we can simply exchange two rows without any bad side effects. Next, we can divide or multiply a row by a non-zero number if necessary. That is, if I want 1 and I say 5 in that spot, I can simply take the whole row, divide by 5. Without any sad consequences. For determinants, if we wanted to do that, we had to take the factor 5 out of the determinant. But for row reduction method of matrices, we can simply do it. We don't have to take anything outside. Nothing. And finally, adding a multiple of one row to another, just like we do with determinants, also is allowed. We can add a multiple of one row to another row. So this is where the difference actually happens. So with determinants, the first two operations very definitely change the value of the determinant, and therefore we need to make these corrections like a minus in front or the common factor taken out in front. With inverse matrix, for matrices, because they are not determinants, these are matrices, for matrices it's not important. Only for determinants, because yes, through these operations, the determinant of the matrix changes gradually. That's fine, because the inverse matrix and the given matrix do not have the same determinant. That's fine. So that's not a problem. All right, now let's do it in practice. So we create this, let me see. Okay, I have simply left a lot of space for this. So let us simply write the matrix Mi, this double matrix. So it's 3, 2, 2, 1, minus 2, 1, minus 1, 1, minus 1. One note though, we can only do this if we are sure that this is not a singular matrix, because otherwise we might get into trouble. Well, basically, if this matrix M is singular, then you will at some point probably get a 0, 0, 0 row. On the other hand, if you want to make sure that you don't do extra work, you might want to start by finding the determinant. At this moment, I am not insisting, but because you will see a problem anyway. However, many people prefer to find the determinant first. In this case, I am just stating, no, you don't have to find the determinant. It is not equal to 0. We will be able to find the inverse matrix, and that's it. Okay, so the identity 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now, to make the identity matrix, to make this shape here on the right hand side, we can do anything of the things described before, even exchange two rows. In this case, I see 1 in the second row, first element. I would like to swap the first two rows. So I would say row 1 is exchanged by row 2. And so I have, instead of row 1, now I have 1 minus 2, 1. Don't forget the right-hand row. The right-hand part as well has to be moved. And now we have row 1 moved to the second row, 3, 2, 2, 1, 0, 0. And then the last row is minus 1, 1, minus 1, 0, okay. 0, 0, 1. There are, of course, always options. There are always options we can do. We might get the 1 in the top left corner here if we want 1 there. I could also do something different. I could say, for example, row 1 minus 2, row 2. Because if I subtract 3 minus 2, I multiply 1 by 2 to subtract from 3 to get 1. Because my aim is to gradually make the identity matrix. And the purpose is we start working by columns. That is, the first aim is to make first column correct. 1, 0, 0 in the first column. This is our aim at the moment, and we will do it immediately. So I will actually leave it here, because what I do now is, of course, row 2 minus 3 row 1 to make a 0 there. And in the third, I will have row 3 simply plus row 1. No, we don't change the sign. As I said, so we don't change the sign when interchanging rows, because I will go back. Exchanging two rows is allowed, and I said it does not do it. We have to change the sign if we are finding the determinant, a certain value. But in this case, we are simply finding the whole inverse matrix, not just the determinant. In fact, when we exchange the rows, yes, the determinant would change, but we are not writing the determinant explicitly. We are not writing down this determinant. The determinant gradually does change through these operations, but we are not showing it. It happens automatically because we are dealing with a matrix. So this is the importance, matrix versus determinant. These are two different things. Matrix is the whole table of numbers. Determinant is one single number, and we are not finding that one single number at this moment. So we don't worry about signs. We don't worry about taking factor outside. Okay. So yes, this is where you have to make the distinction. So you should make a note probably somewhere in your notes that for determinants, we do change signs and bring factors out. For matrices, no. Okay, now I can make these 1, 0, 0 by taking row 2 minus 3 row 1. First of all, I will leave the first row as the tool. As the tool, remember we call them tools. Because I am using the first row to improve the second and third row. It's a tool, so itself doesn't change. Now, all right, let's have a look at this. Times minus 3 plus 3 is 0, minus 2 times minus 3 is 6, plus 2 is 8, 1 times minus 3 is minus 3, added to 2 is minus 1. And now, yes, we do it to the right-hand side as well. 0 times minus 3 is 0, add to 1, still 1. 1 times minus 3 is minus 3, add to 0, get minus 3. 0 times anything is 0, add to 0, still 0. Now the third row, if I simply add now the first row and the third row, I will get a 0 in the bottom left corner. So minus 2 plus 1 is minus 1. 1 and minus 1 is 0. That's seemingly already good. And 0 plus 0 is 0, first row plus third row. 1 plus 0 is 1, and 1 plus 0 is 1. All right, so we have already managed the first column. Now to get 1 in the middle, because for the identity matrix we need 1 there where 8 is. We could, looks like, easily exchange the third and the second row. Yes, you could divide everything in the second row. You could divide the second row by 8 if you like. It's possible, but then you will have fractions. Fractions here, well, they are not very pleasant. So I am simply exchanging these two rows now. So the first row still is the same. 0, 1, 0. Exchanging the two rows, 0, minus 1. Yes, I know I need plus 1 in the end. 0, 1, 1. Don't forget to change that as well. And 0, 8. Okay, that was not a good place to put. As I was trying to look at one place, write in another place, it works well on paper, but it doesn't work with this. So it's 8 and minus 1, and it's 1 minus 3, 0. So yes, I remember I need plus 1 there, not minus 1. But for now, it is, well, I can change, then I need to change the signs of the whole second row. But at first, I would say, let's take row 3 plus 8, row 2, just to get rid of 8. Because we can always change the sign of the second row in the end. That would not be a problem. But getting a 0 there below minus 1 is something that can be done conveniently by multiplying by 8 and adding. So at the moment, 1 minus 2, 1, vertical bar, 0, 1, 0. Second row for now. Okay, for now I can leave it, or I can change the sign, or I can do it in a moment. Now, 0 plus 0, so minus 8 plus 8 is 0. 0 times 8 is 0, added down is still minus 1. Now here, 0 times 8 plus 1 is still 0. 8 times 1, 1 times 8 is 8, plus minus 3 is 5, and 1 times 8 is 8, plus 0 is 8. Changing everything. Now, in fact, I could change some signs, and I will do it, well, in a clever way. Evidently, I will say multiply by minus 1, multiply by minus 1, multiply by minus 1. We may multiply a row by whatever number we like. We don't use column operations because that does not affect the right-hand side matrix. The whole point is we do the row operations because it takes the whole long 6-number row. If we exchange columns, then that means we also have to think about exchanging columns on the right-hand side, and it can create, let's say, confusion. In principle, we could, sort of, but this method will not work later in Gauss method. So we avoid that. We prefer to work with row operations only, because this is mostly for practice. If you want to apply this for finding the inverse matrix, exchanging two columns, not rows, you may, but then you have to think, if I exchange column 2 and 3 on the left-hand side, I must at the same time exchange column 2 and 3 on the right-hand side. If you are sure you won't get confused, then you can do it. In practice, it's simpler, it's easier to do this. Especially, for example, if you want to write, let's say, a program, a code for a computer to do this by this method, and to demonstrate, let's say, the steps on the screen, then you should probably, it's easier to do the same thing over and over again, to focus on doing the same thing. So in this case, if you are sure you can keep track of all the column changes, then yes, but basically better not. And so we could also perhaps change the signs in the third row, but for now, we have 1, 1, and -1 on the main diagonal. 1, 1, -1 on the main diagonal. So as I said, the minus can always be changed to plus. But now we also need to create zeros. It's yellow, yes, it's yellow. We need to create zeros here because we want the identity matrix. So now the next step would be white pen, please, chalk, pen, chalk. Okay, we would say row 1, if we add 2, row 2 to row 1, we will get a 0 instead of -2. So, all right, so for now, I am leaving the bottom part as it is, 0, 0, -1, 1, 5, 8. It's interesting how you develop different habits when dealing with these matrices. I generally prefer to start by copying those rows or columns that are not changed. -1, -1, because these do not change in this step. I leave them as they are. And now the one that does change, second row times 2 added to the first row. So 0 times 2 plus 1. This is why we do the second row now, because the 0 from second row will not spoil 1 in the first row. Now 1 times 2 is 2 added to -2 makes a 0 there. 0 times 2 does not affect 1 at the moment. 0 times 2 plus 1. Now for the right-hand side, 0 times 2 plus 0, still 0. -1 times 2 is -2, plus 1 is -1, and -2 times 2 is -2, plus 0 becomes -2 up there. So pay attention. Yes, we have to change the right-hand side as well. And now what remains is getting rid of this one and changing the signs in the last row. So we will take row 1 plus row 3 now, which will be, okay, I again leave right there. Okay, the second row does not change. It's not touched at all. 0, -1, -1. The last row, I will change the sign in the end. The very last thing to do will be to change the sign of third row. That's for the end. Right now, adding the third row up. 0 plus 1. 0 plus 0. -1 plus 1. 0. Now, 1 plus 0 is 1, 5 and minus 1 is 4, 8 and minus 2 is 6. And finally, the sign change to make 1, we multiply by minus 1, which means minus 1, minus 5, minus 8. So we have options. Of course, we could do basically the same things, basically the same thing, achieve the inverse. This is the inverse matrix. We have found the inverse matrix. 1, 4, 6, 0, minus 1, minus 1, and minus 1, minus 5, minus 8. This is the inverse matrix. This is the inverse matrix. In principle, what we did, we exchanged rows twice. We exchanged rows twice, right? That's what, no, we did not. We did it once. We only exchanged 2 rows one time, which means we changed the sign of the determinant. So if at the beginning the inverse matrix has determinant 1, as we know, then this matrix, evidently, because of this row change, I could even guess it has determinant minus 1. Because we exchanged 2 rows, which means the determinant sign changed. So yes, we can connect determinant to this method. And if I, for example, divide one row by certain number, like minus 1, and I did it twice. So that means I did it for the second row, and I did it for the third row. I changed the sign 2 times. One, this one, and the second was this one, which means the sign of the whole determinant again doesn't change. So when we perform these operations, we can even guess what the determinant of the matrix is going to be. But that's not strictly necessary and required. Change, no. Please do not change rows and columns simultaneously because it is very, very confusing. No, it's best to do one step at a time, or if you want, you can change 2 rows at the same time. You can change 2 rows at the same time using another row as the tool. So you see the row 1, in this case, the tool row doesn't change. We can use it to change 2 other rows, but we cannot in one step like we did here. You cannot do it with row and column at the same time because you will create so much confusion. You cannot keep all the numbers in mind. Changing things in 2 directions, multiplying in 2 directions at the same time is very, very confusing. There are not so many people in the world who can keep track of that. You have heard probably of people who have magical abilities, who can keep in mind the whole phone book, the perfect memory. Well, those people probably could do this. A normal person would be hopelessly confused. So basically choose one row and use it as a tool to change other rows. Basically, we go down, improving a certain column in the matrix. So our direction is always column, column, column. We go down column by column. And interestingly, this is the echelon form. That is, every next column, we start from a lower row. If to improve the first column, we start by using the first row going downwards. To improve the second column, we generally use the second row going downwards because we don't want to spoil the zeros that we already have. That's why we don't take the first row, and so on and so on. If the matrix is bigger, then basically we start every time lower and lower and lower because we don't want to destroy the zeros that we just made. Of course, it would undo all our hard work. So how much time do we have? 4 minutes. Let's see if we can do one more, and that would be it. Yes. Okay. Let's try the row reduction for this. Let's try the row reduction for this. So we can immediately, well, no, all right, I'm writing. No, don't do this. Don't do this. And I am going to do, okay, I'm going to be very lazy. I'm going to write in the identity matrix right now. 0, 1, 0, 1, 0, 0. I think we can do this quickly because this works, I think, well enough. So I will exchange now some rows. First of all, I will put yes, I will, okay, 1 minus 3, 4, and 0, 1, 0. Let's try to do it very quickly, if possible. And second row, 2, minus 1, 0, 1, 0, 0. And the third row, 3, minus 2, 1, 1, stop. This is 0 and this is 1, of course. 0, 0, 1. All right. Now we simply, again, so row 2 minus 2 row 1 and row 3 will have minus 3 row 1. I hope it's not the same matrix. I didn't make, no, it's not the same. Okay. It's not the same. All of a sudden, I thought perhaps it's the same. All right, in the next step. So now we have same one, first row minus 3, 4. 0, 1, 0. Okay, my writing is too large. I can already see problems. Okay, row 2. 2 minus 2 is 0. Minus 1 plus 6 is 5. 0 minus 8, minus 8 is minus 8. 1 minus 0. 0 minus 2. And 0 minus 0. So I did this. Row 2 minus 2 row 1. Now row 3 minus 3 row 1. 3 minus 3. Now minus 3 times minus 3, 9. 9 minus 2 is 7. 4 times minus 3, minus 12, plus 1 is minus 11. On the right-hand side, we have 0 minus 0. We have 0 minus 3. And we have 1 minus 0. Now we see the problem with 5 and 7, how to make 1 somewhere. Now I would like to work on the second column, but it's a little bit problematic. So one way of doing this is, yes, we could divide the second row by 5. That's also acceptable, only it will mean that we have some, let's say, perhaps less pleasant numbers, but it is also acceptable. This is a method that may work. Well, it will work, it has to work. Minus 3, 4, 0, 1, 0. Let's divide the second row by 5. 1 minus 1.6, 8 over 5, right? 0 divided by 5 minus 0.4, that's 2 divided by 5 and 0. So I need to put it more to the right. And now I can think. I can take this new row 2, multiply by minus 7 and add it downwards, which will make a 0 there. So if I take this row 2, times minus 7 and add it down to the third row. Well, we can try. 0 plus 0. See why it's good to take the second row now, so that the 0 doesn't destroy this 0. Now we have minus 1 plus 7 is 0. Now, okay, 1.6 times 7 is 7 plus 4.2. That's 11.2 added to this is 0.2. Okay, it's not so bad. 7 times 1.6 is 10 point, no. 1 moment. 7 and 4.2, 11.2, yes? 11.2 minus 11 is 0.2, so it's not really very bad. Now 0 down, add it down to 0, minus 2 times, minus 0.4 times minus 7 is 2.8. 2.8 added to minus 3 is minus 0.2, again a good number, and 0 added to 1 is still 1. And in principle, now we can go back. We can multiply the third row by 5. Why not? So we can have now 0, 0, 1, multiplying the third row by 5 now. And here we have 0, minus 1, 5. So we can divide by 5, and then, as necessary, we can also multiply by 5 or by whatever number we like. Now the second row is at the moment as it is, 0, 1, minus 1.6, 0, minus 0.4, 0, and here we have 1, minus 3, 4, 0, 1, 0. Like this. Now we can use 1 multiplied by 1.6 to eliminate this number, and multiplied by minus 4 to eliminate this. So we can actually now add this last row multiplied by a correct constant upwards. So it would be row 1 minus 4 row 3 at this moment. So last row for now stays, well, forever, not for now, 0, minus 1, 5. I can leave it as it is. Now multiply times minus 4 and add up. So you see, we took care of the columns going down, down, and down, and now we have to go up and up to get the zeros in the top right triangle. So that's why I'm going through this, but I am using row 3 because these zeros will not spoil 1. The main thing is not to spoil this 1, not to spoil that number. So that's why we are using column 3 times minus 4. So we have, of course, still 1, still minus 3, but now we have a 0 there. And the third row, 0 plus 0 is 0, minus 1 times minus 4 is 4, plus 1 is 5. 5 times minus 4 is minus 20, added up, minus 20. And now to get the second row in order, it seems we have to add 1.6 times row 3. Again, 0 added up will always be 0. 0 added to 1 is still 1. And now 1.6 plus 1 minus 1.6 will be 0. This is why we did this. Now the right-hand side, 0 plus 0 goes up and makes it a 0. I don't like something. I don't like something. Row 2 minus 2 row 1 is 1. This had to be 1, I think. Nope. Row minus 2 row 1. This had to be 1. That's why I was wondering why I had those zeros. I didn't need that many zeros. This has to be 1. This has to be 1. So this has to be 1, and that has to be evidently 0.2 at this moment. All right, so I made a mistake there. I'm sorry about that, and I don't want to keep you longer than necessary. It's time to finish our lecture. So at this point, I made a mistake. So this part will change and some other parts will change evidently. So this is, let's say, I'm using my mistake, my error, to illustrate. And I'm illustrating the fact that it's enough to make one small mistake for this for any of matrix algebra, anywhere in matrices. It's enough to make one small mistake in one element, and you see how everything else will immediately change. Which means you really have to be very, very careful. That's one thing. And that's why we should not change, for example, row and column simultaneously, or two columns mixed in with a row reduction method, and so on and so on. Because it is not so simple as it is. It's just arithmetics, but you have to be good with arithmetics, and you have to be keeping track of whatever you do, which is why it is strongly advisable to write down every transformation before the matrix you write down. Write these transformations down always so that you can keep track of what you are doing there. Because otherwise, it's impossible to find your mistake. You have to do everything from the beginning, every little number, every little step. So yes, it's not the simplest thing. All right. So now, before we finish, people who are here for the first time, perhaps, or people who are not for the first time, but there are still people who have not taken the elementary mathematics test. So unless you do it today, you will be added to the course automatically. Because this is a course that's important, so I will open that test. I will open the test today. I will open it in a few minutes until until the evening. Because otherwise it makes no sense that you are just ignoring something. You cannot ignore something. All right. So I am getting ready to post this and for everybody who has joined the course so far. I am actually closing the option to join today because this is about as much as you can afford to miss in order to still manage the course. And on Friday, we will start dealing with linear systems. Next week, on Monday, we will also deal with linear systems. On Friday, we will already have the first unit test next Friday. Okay, if you need, so those people who failed the elementary mathematics test, that is, got less than 4, are added automatically. If you did not fail, but you think you need elementary mathematics, please email me now. I will join you. I will add you to the course so that you'll get access to the Zoom link. Okay. All right. So now I hope everybody wrote your name in the chat so I can in fact save the chat. Oh, my email. All right, I will write it. I will write the email immediately. It's
Miss, can you tell
simple. It's name
how will the
surname
test
at
for next
Gmail
Friday
or
will be?
at RTU. So okay. Okay. Or the same at RTULV. Okay. Either way, the mail reaches my Gmail. I have set the forwarding from RTULV to Gmail. So you can just as well just write to me directly to Gmail. That's my work email. I only use this email for work. So that's my email. That's generally the first one I open ever. So that's the mail you can reach me. All right. Unit 1, linear algebra. Yes, the first unit test. Of course, we still have 3 methods of solving linear systems of equations. So basically, the first unit test will be about linear algebra. It will be about solving linear systems. But in order to solve linear systems, you will demonstrate matrix multiplication, you will demonstrate determinants, you will demonstrate inverse matrix. You will show everything, actually, you will need everything that we have learned so far. And the unit test will consist of 3 linear systems to solve. How exactly we solve linear systems, what the methods are, we will start dealing with those on Friday, Monday. Elementary mathematics today, yes.
Miss, how the
Elementary
exam will
mathematics
be?
today,
Will it
yes.
be?
So I will perhaps, for now, add the Zoom link to the main page so that those people who are not in elementary mathematics course, who are not added to it yet, can reach it. And then I will add you afterwards, and then you will be able to access it through the elementary mathematics authors page. So I will now put the email link for elementary mathematics, the Zoom link, sorry, also in the main page. Okay, so that you can show up. So I will evidently see you in about 20 minutes in elementary mathematics. I will tell everything about uploads, okay? I will tell everything about uploads. The test will be next Friday. If that's the 19th, then yes. If that's the 19th, then yes.
Miss,
Elementary mathematics,
the
you have
exam.
4 tests. Elementary mathematics is just pass-fail. You do not get a mark. You have to pass 4 tests. Just 4 tests that you have to get at least a 4 for each of those, and that's enough. Then you have passed. It's not a separate exam, it's 4 tests, and everything is fail-pass. All right, I will say goodbye to those who do not need.
Miss, I have a question,
who
miss.
do not need the elementary mathematics. About the exams and tests, I will talk about those as we approach the tests. I am past time. Some people might need rest, and I need to prepare for the elementary mathematics class. I will post important information. All important information will be posted in Ortus. If you have not seen them in other subjects, there is such an element in the Moodle as assignment. And you will be able to upload your work to those assignments. And about retakes, I will tell everything about those, but actually you should read the files I have posted. Course requirements, the schedule, the things that I have posted as PDF files in your mathematics page. If you read those, everything should be clear. All right, I'll say bye for those who do not need elementary mathematics, and I'll see those who do in about 15 minutes. For now.
Thank you.